Quantum field theory. Quantum field theory is a theoretical framework that integrates quantum mechanics, classical field theory, and special relativity to describe the behavior of subatomic particles and their interactions. It has been essential in understanding the dynamics of the fundamental forces and particles that make up the universe, and forms the basis of the standard model of particle physics. Unlike traditional quantum mechanics, which focuses on individual particles, quantum field theory treats particles as excitations of underlying fields that extend through space and time, reconciling the wave-particle duality of quantum mechanics with the principles of special relativity. One of the main reasons for the development of quantum field theory was to incorporate the principles of relativity into quantum mechanics, especially for high-energy processes where particles approach the speed of light. Quantum mechanics alone could not account for the relativistic behavior of particles, such as the fact that no information or particle can travel faster than the speed of light. Quantum field theory addresses this by describing particles as excitations in fields that respect the symmetries of special relativity, ensuring that physical laws hold true even at relativistic speeds. Quantum field theory governs the four fundamental forces of nature: electromagnetism, the strong nuclear force, the weak nuclear force, and gravity. Each force corresponds to a particular type of field, and the quanta of these fields are the particles that mediate the forces. For example, photons are the quanta of the electromagnetic field, gluons mediate the strong nuclear force, W and Z bosons mediate the weak nuclear force, and hypothetical gravitons are believed to mediate gravity, although a complete quantum field theory of gravity has not yet been achieved. Fields are the fundamental objects in quantum field theory, and quantizing these fields gives rise to particles. In classical field theory, a field is a continuous entity that can take different values at different points in space and time. In quantum field theory, these fields are quantized, meaning they exhibit discrete energy levels. The process of quantization allows for the existence of particles as quantized excitations or disturbances in the field. For example, the quantization of the electromagnetic field leads to the existence of photons, the basic particles of light. Particle interactions in quantum field theory are mediated by the exchange of particles associated with different fields, such as photons in electromagnetism or gluons in the strong force. These interactions are represented using Feynman diagrams, which visually depict particle interactions and provide a method for calculating probabilities of different quantum processes, such as particle collisions or decays. One of the earliest and most successful applications of quantum field theory is quantum electrodynamics, a theory that describes how charged particles interact through the electromagnetic field. Quantum electrodynamics was developed by physicists such as Richard Feynman and Julian Schwinger, and is one of the most experimentally precise theories in physics. It explains phenomena like the scattering of light by electrons, Compton's scattering, the Lamb shift, and the anomalous magnetic moment of the electron. Another major success of quantum field theory is quantum chromodynamics, the theory of the strong nuclear force that binds quarks together to form protons, neutrons, and other hadrons. In quantum chromodynamics, the force between quarks is mediated by particles called gluons, and the strength of the interaction grows as quarks move farther apart, a phenomenon called confinement. Quantum chromodynamics explains why quarks are never observed in isolation, and has been critical in understanding the structure of atomic nuclei. Quantum field theory also plays a key role in the electroweak theory, which unifies the electromagnetic force and the weak nuclear force into a single framework. This theory has been pivotal in explaining processes such as radioactive decay. The discovery of the Higgs boson in 2012 confirmed the existence of the Higgs mechanism, which explains how particles acquire mass within the framework of the electroweak theory. Despite its successes, quantum field theory faces unresolved challenges, one of the most significant being quantum gravity. Quantum field theory has successfully explained 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, but has not yet fully incorporated gravity, the force responsible for large-scale structure in the universe. General relativity, which describes gravity, and quantum mechanics are fundamentally incompatible, and efforts to create a quantum field theory of gravity, such as string theory and loop quantum gravity, remain incomplete. Another challenge for quantum field theory is the problem of infinities in certain calculations. When physicists calculate the probabilities of particle interactions, some results lead to infinite values that do not make physical sense. To resolve this, a mathematical technique known as renormalization was developed. Renormalization removes these infinities to produce finite, physically meaningful results, and it has been highly successful in making quantum field theory predictive and experimentally accurate. However, the deeper mathematical reasons for renormalization remain an active area of research. Beyond particle physics, quantum field theory has also found applications in condensed matter physics, where it has been used to study the behavior of quasiparticles, superconductivity, and the quantum Hall effect. Its flexibility as a theoretical framework has made it a powerful tool for understanding a wide range of physical phenomena. In summary, quantum field theory is the essential framework for describing the behavior of particles and forces at the quantum level, incorporating the principles of quantum mechanics and special relativity. Through quantum field theory, particles are understood as excitations in fields that permeate space, with interactions mediated by force-carrying particles. Quantum field theory has been instrumental in the development of the Standard Model, explaining the behavior of fundamental particles and forces with remarkable precision. While unresolved challenges remain, particularly in the area of quantum gravity, quantum field theory continues to be a cornerstone of modern theoretical physics and a fertile ground for further research and discovery across different branches of science.